Thank you very much for giving me the chance to speak here. And the topic is general differentiability, logic, and physics. And this is our common work with Torsten Asselmeyer-Maluga from Berlin. And this is generally about exotic, the four manifolds which are exotic R4. And we consider this as a fundamental fact in mathematics. And, but we propose a different approach than usually is performed within differential geometric books and papers. And this talk is about this approach. Maybe I draw some two facts which can be useful. They are quite general. I avoid the technicalities, but these two facts can be helpful. We have in dimension 4 we can have two compact four manifolds which are homomorphic but are not diffeomorphic in the sense of Hankies theory. So there is trivial, topologically trivial. Let's call this manifold M1. That would be M2. These are compact, and the cobordism is five-dimensional, and it is trivial. It means that the product here is I is trivial, which means that M2 is topologically the same as M2. And the basic examples are given by K3 surface, which is decomposed on one side as 3CP2 and this is in fact homomorphic to K3 surface connected sum to CP2 with reverse orientation. So, so our M1 is this manifold, compact 4 manifold, and this is M2. And the basic fact coming from Hankies theorem is the following, that we always find, specifically for these two manifolds, but in general, this topological product is trivial. But as a smooth manifold, this is non-trivial. That means that it indeed happens that M1 is not diffeomorphic to M2, even though they are cobordant in this sense. So this is the basic fact. If it happens, we always find such submanifold, also compact, let's call it A, and some version of this compact submanifold 8, which is embedded here. But we make inversion on the boundary of this A, and then we always find open neighborhood here and here, such that this must be exotic R4 1 and exotic R4 2. So this is the general fact. This compact submanifold is called Agbulut-Cork, and in our case, this Agbulut-Cork has the boundary which is the homology tree sphere and this is possibly the all technicalities I need here. Just I draw attention to this fact that we, given such non-trivial cobordisms from the smooth point of view, five-dimensional, we always find such a compact subset of this compact M1 and M2, which is embedded into some version of exotic R4 and another exotic R4. And maybe also another technical fact, which is the composition of K3 surface. This is manifold whose intersection form is given by the direct sum of two exceptional by 8 matrices, and then it is connected sum with 3 copies of S2, S2. And the boundary, when we cut out these 3 copies of, when we solder out these 3 copies of S2 cross S2, we cannot have, get a smooth manifold. And the boundary of this E8, E8 manifold is the connected sum of 2 Poincaré spheres. That's all what I need in this talk. Sorry for this drawing. I didn't have on the... And so the general fact is the following, that usual technique from differential geometry, and in general known technique in mathematics in higher than 4 dimension and in lower than 4 dimension, break down somehow in dimension 4. And the byproduct of this breaking is the appearance of this exotic R4. It is a generic situation that when this conflict of technique from higher dimension and lower dimension meet at dimension 4, there appear exotic R4. And we think that this phenomenon is, this is something fundamental in mathematics in general. Maybe we are wrong, but we are working into this direction. And so, in particular, we think that breaking is so deep that the tools based on two-valued logic and ZFC set theory have to be modified. And at the end of my talk, I will tell about physical application of exotic R4. So, in general, the answer to the question if physics needs variable logic is yes, from that point of view. Okay, this is the plan. First, I propose the construction of exotic smooth structure on R4 based on local application of toposes. And then I switch to the discussing of space of all exotic R4 and forcing, set theoretic forcing on such a structure emerging. And then I present some result coming from physics. Maybe coming from dimension 4 into physics, applicable to physics. So in general, I didn't say that exotic R4 are smooth Riemannian, necessarily non-flat 4 manifolds, which are topologically equivalent to ordinary R4. But they are not diffeomorphic to it. And they exist. It was shown in 80s by Friedman, Donaldson, Gompf, Taubes, and some others. And in fact, there are infinite continuum many of different non-diffeomorphic R4s. And moreover, such exotic Rn exists only in dimension 4. And the empirical fact from studying papers in mathematics is that almost all what we know about exotic R4 comes from H-Cobody's theorem, surgery, technique, and breaking of these, in fact, tools in dimension 4, and from Hand-Body's decomposition of our exotic R4 manifolds. And Hand-Body's decomposition typically are very complicated. And for some class of exotic R4, there is a well-recognized structure which is called Casson hand. Here is the simplest Casson hand, which is all of this must be infinite geometric constructions. But the simplest one is drawn here in the Kirby calculus language. And there are more complicated structures. There is always some compact set represented by Kirby calculus and some variety of Casson handles. Here we see only the simplest Casson handles. Usually any tree supports some Casson handle. So this is a very rich world of structures. Okay, our approach, what we propose is the basic observation. Since exotic R4 is a Riemannian for manifolds, there exist, of course, smooth functions on this. And these smooth functions must be differentiable, but they are typically they must be also continuous functions on this R4, which becomes differentiable, smooth, in the exotic sense. So this is very basic, very simple observation. And from that point of view, to grasp exotic smoothness as a variation of differentiation leads us to distribution theory, where similar task was solved. Okay, and but to relate both approaches, I mean exotic differentiation of continuous functions and distribution differentiation of continuous functions, we need topos theory. Okay, let me recall some basic facts about distributions in general. So we have regular distribution, which are represented by some integral function, for example, continuous f. Okay, and then we say that distribution f is differentiable in this sense whenever such integral is well defined, and the differentiation of a distribution f is transposed to differentiation of the smooth test function S, and so on. We can repeat the procedure. There are also non-regular distributions which cannot be represented by any such a function f. The basic example is delta distribution, which is such a linear functional on space of test functions. But even though they don't exist continuous any function, any integral function representing an irregular distribution, they still are generated by continuous functions. And because of the classic theorem by Rudin, we always find such a, for any distribution, okay, it is somehow truncated to the special space of test function, but it can be generalized to general case. We find such a continuous function f and multi-index alpha, where such a differentiation, where this distribution is expressed by such a differentiation, the distributional differentiation of the continuous function f. It is always possible. So distributions are generated by continuous functions and of course are differentiable as distributions, and smooth functions on exotic R4 are generated also by continuous functions, because any exotic smooth function on R4 in values in real values has to be continuous. This is general fact. So in particular, if there is the case that all distributions were regular, we could easily transfer this differentiability of distribution over differentiability of exotic function on R4. But this is not the case, as we know, since there are irregular distributions. However, in the topos, in the Basel topos, which was rather extensively discussed by Rysiek yesterday, all distributions, Okay, but you didn't mention that. In the Mordic Reyes work, book about smooth infinitesimal analysis, the Basel topos supports such correspondence between such effect first, maybe, that for every distribution in the topos B, there exists a function which makes this distribution regular in this topos. And of course, we know from the other side that to support such result, we need to make a switch from object of natural numbers, which is standard, let's say such, to the object of smooth natural numbers, which is non-standard. And without this switching, we cannot prove that theorem. And moreover, there is one-to-one correspondence between distribution in set and this internal distribution in the topos B. So this is our technical environment where we want to recognize exotic smoothness on R4. In general, to recognize exotic smoothness on R4 is very difficult task and unsolved yet. So this is not just if it succeeds somehow, we get some good results. Okay, so let me define the categorical smoothness. Starting from any smooth manifold, let's say Mn, with its open, smooth, good atlas. Good atlas means that the common part of these two local patches is diffeomorphic to R4, and also any of these patches is diffeomorphic to R4. And so there are transition functions, and let us require that at least one of such local U alpha belongs to a Basel topos. So just we define such a function which changes at least one of such function of such a local open neighborhood as leaving which sends this neighborhood to the Basel topos. It can be done by embedding of smooth manifolds in the Basel topos functor S. So this is not that it is easy to be performed. By the way, there is a good question about since any smooth manifold is representable in Basel topos, how to recognize this specific exotic R4. But I don't want to develop this question, but this is very basic and a good question. Okay, but maybe not now. And we require that there exists at least one such U alpha, but not all U alpha are embedded in the Basel topos. And this very simple requirement give rise immediately to the following statement that if every open smooth cover of Rn has the above property, what I mentioned just before the moment, then this Rn has to be exotic smooth. Of course, this can happen only in dimension 4, because exotic Rn exists only as exotic R4. And the proof is very easy, very basic maybe, that if indeed every smooth open cover of Rn cannot be reduced to a single map, such a manifold cannot be standard smooth, because if it is standard smooth, it is diffeomorphic to a manifold with one cover. So we exclude such possibilities. So this kind of smooth manifold must be exotic. So this is of course just observation which motivates us to go further and to ask the question whether this B-generated smooth R4 is relevant to actual exotic R4 which we know from differential geometry, and especially which we know from hand decomposition manipulation, which are very involved. or maybe we are aiming at a completely different smooth structure on R4. Okay, I will say something about this different smooth structure on R4 maybe later, but right now it is possible to prove the following theorem, that if we trace the effect of such smoothness structure, which is modified by previous construction, if we trace the effect of this construction in set, the resulting smoothness structure cannot be diffeomorphic to the initial R4, which we started with. So we have, in principle, machinery or procedure how to produce non-diffeomorphic smoothness structure by the use of Basel topos applied locally on manifold, which are not diffeomorphic to the smoothness structure which we started with. And we don't use here handbodies. Of course, we don't know, maybe not of course, but we don't know whether the resulting smoothness structure are always non-diffeomorphic. We don't know this, but we try to get some result into this direction. Okay, what about if this construction would lead to some new exotic structure on R4, because we don't use handbodies and we don't use known technique from applied so far, and what that means, and if there is really a place for such structures. And one particularly interesting point is exotic S4, exotic spheres, the four-dimensional spheres, which we don't know they exist, because it is still open smooth Poincaré conjecture in dimension 4. In dimension 3, it was resolved by Perelman, but this is not solved. And we know that if such exotic spheres exist, they require a completely different smoothness structure on R4. When we remove one point from this exotic sphere, we get exotic R4. But this is completely different story with any known exotic R4 so far, because when we compactify, when we make one-point compactification of exotic R4, which we know, we get a standard S4 always. So this smoothness, this smooth R4 obtained by removing one point from here must be completely different to what we know up to now. So that's why our approach maybe is not void, but of course, if we are really able to attack this problem, it is something, but we don't claim that. This is just a rough idea, maybe something is in this. Okay, let me switch to discussing the space of all small exotic R4. Small means that they are embeddable in the standard R4 as some open subsets. Large means that they cannot be embedded in R4 because there exists some compact subset which is not embeddable. But we don't need these technicalities here. The simplest Casson handle is represented by a sequence of, for example, plus minus integers. And we know that such a simplest Casson handle, which is represented by +1, +1, this is the way how some geometric submanifold cross in these four manifolds. But we don't need to know the particularities of this construction. But that can be positive crossing and negative crossing. So the sign is +1 or -1. And if any crossing is positive, like here, this is infinite, necessary infinite sequence. Such a Casson handle is exotic, and moreover, it if it is glued in to the compact set, this A here, we obtain exotic R4. So this is this we know right now, that using such Casson hand, which is the simplest, as the result we obtain exotic R4 as the result of gluing to the Agbulut cork. But in general, any such sequence corresponds to some Casson handle. And it is still open question which such sequences, which such Casson handles represented by such sequences when glued to A give rise to exotic R4, and which are non-diffeomorphic exotic R4. This is the open question, and we want to shed light on this problem using set theory in this respect. So we have such a question: which different sequences corresponding to different Casson handles give rise to exotic R4, which are moreover non-diffeomorphic? And okay, this is of course a difficult problem and still open. That's why we propose to relativize our constructions to models of ZFC, especially to counter models of ZFC, because any sequence of plus minus numbers can be transformed to 1, 0, to binary representation of any real number. So from that point of view, any Casson hand corresponds to a real number. And moreover, for M be a counter-transitive model of ZFC, there is always a Cantor set or Polish space representing the real line in the model. And so we have the correspondence between real numbers in the model and Casson handles in this model, and we would like to extract some information about exotic smooth structures on that base. So one technique known from set theory is a forcing extension of the model, especially Cohen extension, and everything what we need to know about this Cohen expansion is that there are some sequences of 0, 1 numbers which are not present in unextended model M and are already present in extended model M over G. And this G is represented also by some sequence. So the general facts about real numbers in model M and in model M over G, an extended model, is the following: that this model M is a submodel of this extended, but is not equal when the forcing is non-trivial. And the real numbers in M are proper subset of real numbers in MJ, and the real numbers in M are Cantor set in M, also Cantor set in MG, but this Cantor set represented in this extended model contains more branches than this Cantor set. This is a binary tree representation of Cantor sets. And also the extension of the real line does not cover, because this is still countable, does not cover all real line in reality. Okay, which sequences from these real lines in extended model are not present in the non-extended model? They are certain Casson handles. Whatever they are, there are sequences of 0, 1 numbers, and they must be represented by certain Casson handles. So we have a direct conclusion that this set theoretical consideration allows us to speak about Casson handles which are present in the model, in a Cantor model, or non-present. And we can rephrase this, that the extended model sees this extension by G as a Casson hand, some Casson hand which is not present in them. Similarly, subsequent extension sees another sequence as a Casson hand, and this is non-present also in the previously extended M over G model, and so on. So we can iterate this procedure and obtain a sequence of Casson handles which are seen by non-extended previous model. Also we can prove that this is the fact that the M sees uncountably many different exotic R4. Cs means that we can prove that in M there are uncountably many different exotic R4. This is similar as even though M is a countable model, we can prove that there are uncountably many real numbers in the model. But from the outside, there are countably many. Similar is to different exotic R4. In M, we can prove that there are uncountably many of them, but from the outside, there are only countably many in the model M. And now we phrase the following question. Which forcing extension do lead to different non-diffeomorphic R4? We know that each forcing gets a Casson hand, but it can, of course, happen that the extended model see some of these Casson handed as diffeomorphic. So it seems that such a question is equally complicated as original question about making classification of exotic R4, especially with relation to Casson handles. But there is one profit from using forcing approach and counted model here. Namely, this is the Hankies Theorem, stating that it can happen that there is no model of ZFC in which one can see forcing extension and diffeomorphism of resulting R4. This theorem is stating here. So for every counter-transitive model M of ZFC, there always exists two forcing extension of M, such that they cannot be submodel of any single model N of ZFC with the same ordinals. This is the limitation of this procedure. But we require the ordinals are untouched. On the other side, it is interesting question what that means to exotic smooth structure. Then we move ordinals. This abstract maybe problem. So we have the following situation. Starting with any counter-transitive model M, we create two incompatible Cohen extensions, which are again counter-transitive models. Then we repeat the process, and incompatible in the sense of Hankies theorem. Then we repeat process and find further incompatible Cohen extension, and so on and so on. So we get a counter set of such extensions. And moreover, this counter set of extensions is generated by any model of M, any model of ZFC, any counter model of ZFC. Changing M, we get homomorphic copy of a counter set. And there are differences between counter sets from the inside of the model, where we see Casson handles and real numbers in this model and non-present in another model. But from the outside, these all are counter sets which undergoes homomorphic transformation when changing counter model M. And the general situation is the following. Taking the Cohen Boolean algebra, which is the completion of the counter atomless, the unique counter atomless algebra, so-called counter algebra, which I ask shown about. When we are taking regular open subset of a Cantor set, so we obtain precisely this Cohen algebra AC. And then homomorphisms of a Cantor set are one-to-one to the automorphism of this Cohen algebra. And moreover, any automorphism of this Cohen algebra leads to automorphisms of such special algebra which are subset of natural numbers modulo finite subset in some sense. But this is known to be atomless algebra, and there are many very interesting questions about this thing in mathematics in general. And on the other, homomorphism of Cantor set leads to automorphism of p omega over phi. On the other side, there exists universal exotic R4, which contains all other known exotic R4 so far. So that construction would mean that trivial automorphism, should correspond to diffeomorphism of this this universal R4. Trivial automorphisms are such that they correspond to some permutation, or we say almost permutation, up to finite subset of natural numbers. If there are automorphisms which don't correspond to almost permutation of natural numbers, they are called non-trivial. It was proved probably originally by Rudin also, that under a continuum hypothesis there exists non-trivial automorphisms of p omega over phi. So the situation is following. Trivial automorphisms should correspond to diffeomorphisms of this universal R4, and if exist exotic S4, the non-trivial automorphisms of p omega phi probably correspond to some exotic R4 obtained from this sphere, maybe also universal. We don't know much more about this, but we have some arguments that it should be really something like that. This is conjecture. Okay, let me switch to the last part, which is exotic R4 and physics. And recent result by Etesi shown that large exotic R4 are gravitational instantons. So, as the conclusion, any theory of quantum gravity, which is quantization of general relativity, has to deal with such things. Another thing is that the small, tiny value of the cosmological constant, which causes the expansion of our universe, accelerating expansion of the universe, can be explained as a curvature of exotic R4 embedded to K3. Precisely this exotic R4 embedded in this K3 here. K3 connected some with reverse orientation CP2. And we have really proved that, and it is interesting result. Moreover, this tiny value of the cosmological constant is a topological invariant. And also some other physical parameters can be obtained as a topological invariant basing on this specific exotic R4 embedded in K3 connected some with CP2. I have just shown the results, not explaining much about this because it's too much, but really this A is the Arc-Bulut quark here. The boundary of this Arc-Bulut quark is sigma 257 is here, and we have Chern-Simons invariant of this sigma 257, which is precisely this. And P plus 2 is a connected sum of two Poincare spheres, and Chern-Simons invariant of this, which is here as the boundary of E88 part. And so we were able to prove that such expression really gives rise to realistic value of the cosmological constants. And this CC is a topological invariant, of course, up to some physical constants, because otherwise we don't have connection to physics at all. In this K3, in this embedding of exotic R4 into K3, precisely here, this is exotic R4 embedded in K3, there appear two topology changes in the body of K3. And there are three-dimensional topology changes. First is from 3-sphere to sigma 257, which is the boundary of Egbert Kork. And the second one is from sigma 257 to the boundary of this E8 factor. And when we take the initial radius of this sphere here as a Planck length, then we get physical conclusion. So we, especially, for example, there is energy assigned to this first topology change, which is of order of a good energy, which is also topologically supported. And if we are working in the case of second topology change, we get also, and it is the composition of K3 ciphers, which is here. We obtain, we obtain also the energy scale, which is this time of the average about the weak electroweak scale. And these quantities are also topologically supported. And what we get, we can also get from topological considerations the change of the scale and the expansion, acceleration, expansion of the space with n-folding given by 51, which is also accepted by current cosmological observation. We just made this calculation and collected the results, and we just look at them, and it doesn't mean that we understand what that means, that we get the number. And also in the Starobinsky model, which describes accelerating expansion of the universe, there is 3-parameter alpha, which this time can be expressed as a topological invariant in these units of Planck length. And also spectral tilts and tensor scalar ratio are also topologically supported invariant. Okay, so our position is the following, that when juxtaposing known mathematics from dimension higher and lower than 4, it appears a kind of discontinuity. And so that means that we need 4 new methods. And, but in general, the variety of conflicts always result in existence of exotic R4. It is quite strange situation. That means that such exotic R4 appear as some generic objects in this contact region in mathematics. We suggest that the structure of exotic R4, this conflict is even deeper and is extended over logic and set theory. In our opinion, this sheds light on the existence and the shape of exotic 4 spheres. And this is quite surprisingly that a model of expanding universe based on such exotic R4 is realistic. Thank you very much.